Welcome back. In this video, we'll start with a short recap of linear regression with multiple features, also called multivariate linear regression, and then we'll extend our knowledge of multiple features to gradient descent. So, at the end of this video you will have a generic gradient descent algorithm that is able to work with as many features as we desire. To recap, we saw that we can write a general hypothesis for linear regression that has n variables or features. We saw that we can rewrite this long expression in vector notation. More specifically, in theta transpose times x, with both theta and x being vectors of dimension n+1 and with x subscript 0 always being equal to 1. Now we will look at the cost function for multiple features. Actually, the only thing that changes when we extend the cost function from one variable to multiple variables is the hypothesis itself. The notation, however, stays completely the same, except that we now not call it j of theta 0 and theta 1, but we call it j of theta 0 up until theta n. Or we can express it just like j of theta, with theta being a collection of all theta parameters. Also, for gradient descent, we get a similar expression as the one from one variable. The only thing that changes is that we now use a cost function that is dependent on theta 0 up until theta n. And that we not only need to do a simultaneous update for theta 0 and theta 1 but also for all other parameters. In fact, the only thing that changes is the derivative part. Like we saw before, these are the two different derivative parts for respectively theta 0 and theta 1. But now that we work with multiple features, we can't write x superscript I anymore, as this will include more than one feature. Thus we must define it as x subscript 1, superscript I to define the first feature for the ith training example. If we extend this for more features, we notice that we get each time a fairly similar term. In fact, as we know that x subscript 0 is always equal to 1, we can add this over here, and now we really see the similarities between all these equations. In fact, we can now write one general gradient descent algorithm that works for both linear regression with one feature and with multiple features. So to summarize, we just created a general equation for the hypothesis, the cost function, and the gradient descent algorithm. Or in other words, n will define the amount of features we have and whether that is 1, for linear regression with one variable, or whether n is larger than 1, thus for multivariate linear regression. In both cases we can just use these general notations. If you have any questions, please leave them in the comments below. Thank you for watching, and I'll see you in the next video.